Hello everyone. For those of you who don't know me, I am the volunteer coordinator for Story Brymbo. I'm also a geologist by training. So in 2019, I quit my full-time job to volunteer at Story Brymbo, and that led me to the opportunity to study a PhD on the fossil forest at Brymbo. 3.5 years later, I came back here, got the job as a volunteer coordinator, started in June. I'm going to do a whistle-stop tour of deep time that we covered in my geology course that I ran for volunteers in October. And then I'm going to quickly tell you about what I've been doing for the last 3.5 years for my PhD. So this is a geological time as we know it. What we're bothered about today is the blue bits and the purple below it. That's the Paleozoic, really old stuff. These numbers here are millions of years old. So we know Brymbo fossil forest is 314 million years old. So that's where we're sitting there. Anyone want to guess, who was not on my geology course, what these numbers mean? Years? No, the years are these ones. So something happened a few times that caused me to put those numbers there. I heard someone whisper it. Extinction events. So those numbers I put on there are the percentage of life on Earth that was destroyed in those extinction level events. So it was not a nice time to be on Earth, those few 100 million years. And you can see just after Brymbo fossil forest, at the end of the Permian period, 95% of all life on Earth was wiped out. So pretty crazy times. The UK, where we are now, in the Northern Hemisphere, throughout 500 million years of history, we've come a long way. We started off in the Southern Hemisphere, near where Antarctica is, and we collided with a couple of different tectonic plates. In the first one, we met Scotland. That's when Wales and England met Scotland, and that's what we went to look at as part of the geology course. So on day one, so this drone footage was taken by Jonathan, who's here tonight. This is a quarry down in Shropshire. Right, so this is the quarry we were looking at. The pink rock is a granite that cooled under the Earth's surface about 600 million years ago. So life, as we know it, was just about developing eyes at that time. This is mega old stuff. It's probably some of the oldest rocks you can see from around here. After 50 to 100 million years of time, these rocks were deposited horizontally at the bottom of an ocean. When we collided with Scotland 500 million years ago, these things were crushed, crumpled, and became mountains and have eroded over 500 million years, and we're lucky enough to look at them today. And if you don't believe me, we went just around this corner here and we can see ripple marks. So these are the ripples that were on the ocean floor 500 million years ago. Pretty incredible stuff. You can't see that in many places in the world. Here is the group pretending they're on the Cambrian ocean floor. Okay, day two, we went to Llangollen to look at the limestone. So this stuff, we've skipped about 200 million years, and now we're into the Carboniferous period where Brymbo is. So at the start of the Carboniferous period, North Wales was under the sea. It was near the equator, it was nice and tropical, and we had coral reefs forming and limestone forming. We visited this locality, which tells the story of beach sediments tilted, turned into river sediments, and then 100 metres above this-ish became the swamps where the Brymbo fossil forest is formed. So this site tells the story of North Wales moving from in the ocean onto land. If you want to know more about this, maybe I'll be able to do a geology course number 2. Sign yourselves up. Okay, now I'm going to hit you with some science. So for the last 3.5 years, I've been studying through Bangor University, their biology department actually, looking at the fossil forest. So that's the title of my thesis. I submitted it in June, and I've got my viva to defend it on Monday. Scary times. So the first step of this process was to figure out if the rocks in the coal hosting sediments that we have around here, find out their history, how deep they've been, and what temperature they reached in the Earth's core, to know that what I was planning to do was relevant. So me and Peter spent 2 days finding coal seams around North East Wales. I don't think anyone else has got a misspent youth like Peter that could show us the places we went to. We were crawling around ditches and in riverbeds. So we found 9 coal seams in total in the area. With some data magic that I won't bore you with, I was able to come up with this plot. So the green line is basically the Earth's surface over time, and the blue is where the rocks that we're standing on now have travelled through their 314 million years. So they were buried really quickly, and they reached about 118 degrees C. Now, what I was worried about was anything over 120 degrees C wouldn't be relevant for the techniques I'm about to talk about. So luckily for me, these rocks have been not baked just enough for me. And then I plotted this fancy history of how the rocks have been buried and eventually reached the surface, and we see them there today. So my first port of call was the siderite. So these are nodules that we have in the fossil forest. Siderite is iron carbonate. It's basically a mineral that has formed between the sand, silt and mud grains that make up the Brymbo fossil forest sequence, and they're everywhere. They're all over the site. This is one that is saw in half. And they come in all shapes and sizes. Some have got little bits of plant material, those little black specks you see of plant material. Some are really pure, take up a nice polish. Some have layering in. Some have little bits, I think these are old burrows, so little fossils in them. So you're probably thinking, what's he talking a load of crap for? You wouldn't be far wrong. So what I found when I sliced these rocks up is they are made up nearly completely of poo, microscopic poo. So when I looked at them under a microscope, so these are under a scanning electron microscope, so what you're looking at is absolutely tiny. And they are chock-a-block of these little pellety things. I spent a lot of time trying to figure out what they are, and I think they're just a load of crap. But these are really important because these bits of poo were settling in this swampy environment. Bacteria was eating away at that poo, and they themselves were pooing out the chemicals required to form siderite. And that is important because we can thank siderite for some of our best fossils. So the siderite formed and encased the fossils and protected them from being squashed and damaged too much over time. And that's why you can see we have absolutely stunning fossils with the veins still attached, leaves still attached to stems, and that's all thanks to siderite, which is thanks to these crazy processes that were happening. It's even a miracle that they exist the more you look into it. Okay, and then I moved on to looking at the geochemistry of the plant fossils. So the plant fossils we have are preserved as a carbon film. And my first job, if I wanted to analyse this carbon film, was to remove the black carbon from the surrounding rock. And that was easier said than done. So I put my mad scientist hat on, went into the labs at Bangor and started dissolving rocks in acid. So I dissolved them for about 3 days in really strong acid at about 50 degrees C. In the end, after I rinsed them off a few times and washed them off, I was left with this rubbish. I had to then, see the little black flakes in it? I had to extract that from the clay crap that wouldn't dissolve in the silt, in the acid. So, after a lot of trial and error, there's this stuff called zinc bromide, and if you mix it with water, it makes a really thick, dense water. So I made a solution that is about twice as dense as water that you'd drink. And because carbon is really light, I plopped these bits of rubbish in this dense water, left it for a few days, and the carbon flakes settled at the top. And that's how I was able to separate it. Took them off, sent them off for analysis. I've got to give you a bit of background about stable isotopes. Don't get scared by that word. So carbon comes in 2 flavours, carbon-12 and carbon-13. They're different at an atomic level. You don't need to worry about that. But basically, carbon-13 is ever so slightly heavier than carbon-12. And that's what's important. So when plants photosynthesize, they're sucking in CO2 and they're putting that carbon that's in CO2 into their plant tissue, and that's what makes plants. And the plants at Brymbo are doing the same thing that plants do today. So plants that are just chilling, having a nice time, not having to worry about water, they've got plenty of water with them, they have to put less energy into photosynthesizing. And they end up with more of the lighter carbon-12, so therefore less of the carbon-13 because it's heavier. Plants like a cactus or something that doesn't have as much water, they're struggling. They have to put the effort in to photosynthesize, and they end up with more of the heavier carbon-13 in their plant tissue. And the ratio of carbon-12 to carbon-13 is preserved in the fossil record. So I can measure it from those bits of carbon that I extracted from the plants. And that can tell me about how much water the plants at Brymbo had access to. No one's done this before. So I analysed 3 different types of plants. The first one are the calamites. These are the giant horsetails. Some of you probably know horsetails or mare's tails that they grow in your garden today. These gave me values that suggested these plants liked wetter conditions. I expected that, makes sense. The ferns, I measured them, and they, again, pretty wet conditions and really tightly grouped. So we know that the ferns liked a particular type of water condition in their environment. Now the interesting one was the lycopods, which is the star of our show at Brymbo. These are the big standing trees that we get. And interestingly, they plotted from wet all the way to dry. Now this has never been seen before and suggests that these lycopod plants, we know they lived longer, but they were able to adapt their photosynthetic method to put up with having less water. And these may have been the first plants ever to evolve an ability to adapt to changing water conditions. This is a mangrove swamp on the earth today, and this is the depictions of what people always say the Carboniferous coal forest looked like. And many of them probably did, but not Brymbo. We did not have standing water, because if we did, those lycopods would not be showing me numbers that represent that they had to adapt to drier conditions. So what we got at Brymbo is some special conditions where normally we just have lycopods growing, so the big trees would be growing in a well-drained soil, and they were able to adapt and survive in that environment. Every now and again there was a river nearby, couldn't tell you how far, and periodically that would flood. And it might flood for a long time and bring in a lot of sediment, and you might have minor river channels that flow through Brymbo, and we can see them in the sediments that we've got on the fossil forest. While those minor rivers were flowing, the other plants, so the ferns and the horsetails, could grow when that standing water was available for them. When that minor channel receded, we'd go back to normal with just the lycopods growing. So Brymbo Fossil Forest is special because it represents the sort of extremes of what these plants would be comfortable with. And that, combined with those crazy chemical situations that were going on forming the siderite, is why Brymbo is so unique and a one-off in the world. Thank you, everyone.